A very good evening to all of you. So we'll be taking some numericals on the unit number 1. So these numericals are on the steady state stability. You have studied the four quadrant operation of an electrical drive. So basically we have to understand the steady state speed of the electrical drive system. Now as you know that there will be two torques, that is the motor torque and the load torque. So when the motor torque is higher than the load torque, then the drive will get accelerated, and when it is less than the load torque, so what is going to happen, that the motor will de-accelerate. So the motor will attain a steady state only when the motor torque characteristic is equal to the load torque characteristic. So based on this concept, we'll try to solve some numericals, which is very important from examination point of view. So now in this question, what is given? A motor is used to drive a hoist. So basically the application, or you can say a load, is a hoist, and the motor characteristics are given by. Now you can see here the quadrants are given, and in this quadrant the motor torque is given. So what you can see, that when the hoist is loaded, the load torque will be 100 Newton meter, and when hoist is unloaded, so that time the load torque will be minus 80 Newton meter. So you will have to calculate the equilibrium speed in all the quadrant. So whenever you have to calculate the equilibrium speed, that time you have to equate the motor torque equals to the load torque. So we'll see that the quadrant 1 and 2, the T will be equal to this, and for the quadrant 3 and 4, T will be equal to this. There is a correction in this question which we'll have to do. So now we'll take the quadrant number 1. So for quadrant number 1, this motor torque we will have to take, and the load torque when hoist is loaded. So you can see that I think you will have to recall the concept which we have studied in the class. So that time TL will be is equal to 100 Newton meter. That is, the load torque should be positive. So T will be equal to Tm. If you solve this, then you will get the speed of the drive, or you can say the speed of the electrical drive system. Now, similarly for quadrant 2, I think it is for the braking operation. You can see that this is a braking. So regenerative braking, that is the forward regenerative braking, will have to take into account. So in that case, load torque will be minus 80 Newton meter. So if you solve this, you will get the speed. Now similarly for quadrant 3, so you can see the quadrant 3 is T will be equals to minus 200 minus 0.2 Newton meter. It means that the motor is going in the reverse direction. So that time the motor torque is also reverse. So TL will be equal to minus 80, you will have to take. Fine. So this will be, N will be equal to minus 600 RPM. If you solve this, you are going to get this value. Now in the quadrant 4, it is a reverse braking. The motor torque is negative, but your load torque has become positive. This we have studied. So if you solve this, you are going to get N will be equals to minus 1500 RPM. This is the first numerical, which is very important. Now, the second one we will try to understand. Now, here you can see T will be equal to the motor torque is given to you. Then the load torque, it is 3. It means that the torque is dependent on the speed, and there is a relation between the motor torque and the speed of the drive. And similarly, load torque is again dependent on the motor speed. Now here you will have to find the equilibrium point and the steady state stability. So I think in the lecture only I told you that the slope of the load torque, if it is higher than the motor torque, then the speed will be a stable speed. Because if you just apply the perturbation, what is going to happen? If you just apply a perturbation, if you increase the speed or decrease the speed, then you will have to check whether the drive is stable or not. So this is the condition for a steady state stability. Now, if you find the motor torque slope is higher than the load torque, then that motor will never come back to its initial state. That will enter into the unstable state. So to find the equilibrium point, T will be equals to TL, just because you know equilibrium point means that motor torque equals the load torque. So T will be equals to TL. So 1 plus 2 omega m, 3 under root of omega m. So here the square root is given. So you will have to free this term. So in that case, you will have to square the both the side. Now after squaring, what you are going to have? You are going to have the quadratic equation. So you just have to solve this for m om square omega m square, then minus 5 omega m plus 1. So what? So you will have to write this minus 5 omega m as minus 4 omega m and minus omega m. So if you solve this, you can solve by using a calculator also. So omega m will be equals to 1 and omega m will be equal to 0.25. So you are going to have the two equilibrium points. So for omega m, you can calculate the t value, and similarly for omega m, you can again calculate this value. So you will be having the two torque, but you will have to find whether this is stable or not, whether this speed omega m will be equals to 1 radians per second. If it is stable, is it stable or not? And again, you will have to check for this. Means which speed is stable. I think we have also done this in our classes. So for that, this is the condition. It means that dTL upon d omega m. It means that you will have to take the differentiation of one. So because for finding the slope, you need to have the differentiation concept. So dTL d omega m 3 under root of omega m. So after taking a differentiation, 3 upon 2 under root of omega m. Is it okay? Then again, dt, if you can solve this, then here you will get, because one is a constant value. If you take the differentiation, you cannot differentiate further. You can integrate this, but you cannot differentiate. So it will be 2 only. So now you will have to check whether the omega m will be equals to 1 is stable or not. So here, put omega m will be equals to 1, 3 upon 2 under root of 1. So this is dTL upon d omega m, that is 1.5. It is 2. This is 2. So you can see that this slope is higher. So I think this is the unstable point, because motor torque, if it is higher, the slope of motor torque, if it is higher than the load torque, then the motor, or you can say a drive, will never come back to its initial state. It is either it will increase or it will decrease. Now, similarly, you will have to examine for this point. I think this is coming around, this is higher than this DTL is 3, that is higher than 2. So in this way, you can find whether the point is stable or not. This is your second one. Now, similarly, you can go for this third equation. I think this is the same thing which we are doing. Again, you can see that, right. This is the fourth numerical. This is the fourth numerical, which I think this is right. So this is the question number 5, which we have to understand. Now you can see that there is the torque equation, and it depends upon the speed. So linear speed is given to you, and TL will be equals to 100 Newton meter and TL minus 100 Newton meter. This is the initial value, and this is the final value. So you will have to calculate the speed for both the values, because you will have to find the initial speed also and the final speed also. So you just have to equate the TV will be equals to TL. So you are going to get this 500 RPM, and here you are going to have the 2500 RPM. So in this way, you can calculate the you can solve the numericals of the first unit. This is all about for today's class. We'll meet in the second unit. Thank you.